All right, so we're going to look at integration here, but we're going to break up the pieces a little bit into talking about what integration really means. So you're going to run across problems like this, and I like problems like this for a couple of different reasons. One of which is it really does a really good job of emphasizing what you're doing with integration. So the goal here is to identify what the integration from 1 to 3 of f of x is. And remember that dx is kind of like our adverb here. It tells us what we're integrating with respect to, and I'll work in another example in another video that explains that in a little better detail. But the idea being is that we want to figure out what this is. Now remember, integrations from a to b of some function, f of x, g of x, whatever, is a total of some sort. A total area, total sum, total whatever. It's just a total. And most of the time what we're going to evolve back to is just so we have some generic looking function there. Here's A, here's B. What we're finding is the area between that curve and the x-axis. We're actually going to do some as well, where we're finding the area between two curves even. And that's more or less the exact same process of what we're doing here. It kind of emphasizes it in a different way though. So this is what we're doing. We're finding that area. So let's just say what we are doing here is that we know that the integration from some function, we'll just call it this looking thing here, is going from 0 all the way up to 3. All right, we're finding all of this right here. Okay, so that's that total from that section. This one, it'd be the same graph. I'll try to draw it as best I can to match. Pretty close, right? And on this one, we're going to 1. So we're going from 0 to 1 there, right? So if what we're looking for is from 1 to 3, the thing that we're wanting this to be, so the integration from 1 to 3 of f of x dx would be that same curve, whatever that curve is, and I'm drawing it as a straight line, but just pretend it's just some curve. You're going from 1 to 3 there, all right? But if you're going from 1 to 3 and you're wanting this space in between, we know this one, we know that one, so it has to be 0 to 3 minus, and if we think this, here's 1 right here, right? We're going from 0 to 3, and we know from 0 to 1, then this has to be whatever that other piece is. So this area was 8. This area was 2. So that means this area right here has to be 8 minus 2, because we're just taking off that piece in the front there, which gives us 6. So integration from 1 to 3 of f of x dx is equal to the integration from 0 to 3 f of x dx minus integration from 0 to 1 of f of x dx. All right, which means that we're doing 8 minus 2, which is 6. And that's what you're doing when you do integrations, and you can break this up into as many pieces as you want. And this is quite useful because let's just say for a second that instead of it being a problem like this, what if we're dealing with a problem that looks more like this? And that's our function, right? And of course, this is what we'd call a piecewise defined function. And we wanted to find the integration from 0 to, let's call this spot right here, say 5, right? Well, we could do, and we could break this up and let's say this is 2, we'll call this 3, here's 4. It's not very symmetrical, but use your imagination, right? So if we wanted to find that area from the integration from 0 to 5 of whatever this function is, let's call it g of x just to be different, right? This whole curve here is g of x. We want to find that area that's under that curve. We can break that up from 0 to 1 of g of x. And we can go from 2 to 3. And I'll talk about why I'm splitting it up this way in just a second. And then I can go from, sorry about that, from 3 to 4. And then I can go from 4 to 5. Now I'm breaking it up that way in those pieces because this looks, sort of split these up, kind of across these fault lines, if you will. This piece right here looks like a trapezoid. This looks like a rectangle to me. Here's another trapezoid. And this is defined by a curve. So that'd be our curve section, if you will. So hopefully we have a function of some sort that defines that particular part of the curve so we can figure it out. But these other pieces, it'd be just as easy to find the area of the trapezoid given, assuming that we know what these locations are. So let's just say that we know that this piece right here, or that point, is 2, 1. And this point right here is 3, 1. And this spot right here is 4, 1, that's kind of small in it. Let's make this 2, 2, and we'll make this 1. There we go. Right there. Now everything will fit in there. So we have these trapezoids that we can look at. And this first trapezoid would be 1/2, the base 1. Well, this would be this base 1, so we need that spot right here. So let's call that 0, 1 there, right? So that first height right here would be a height of 1. And then a height or a base of 1 and a base of 2, so it's 1 plus 2. And then the length, which is 2, or the height of the trapezoid, is going to turn on its side there. And then you have the next one, which is a rectangle here. So that is 2 up and down and 1 across. So it'd be 2 times 1. Then you have your next trapezoid, which again is 1/2, base 1, which is still 2. This is 1. So this is 1 plus 2 again, times the height this time, which is 1. And then plus this last little piece here, whatever that is. And so that'd be in this case, to get the exact value, we'd have to do the integration, which means we'd have to know what that curve is, whatever that is. And we'll get to that little piece later, but then we could just find the sum of those. And that's why this is useful to us, is because if we know individual quantities of the curve, quote unquote, as we go through that, then we can find the volume, the area, the total sum, the amount of money spent, the number of people that go through the turnstiles, whatever that function is representing, we can find that simply by looking at individual time intervals. Let's think for a second. This is talking about people going into a stadium. And it's a fairly consistent process as people go into the stadium right before the game, and then there's this rush right before the game starts, and then after the game starts, there's a decline. And I don't know what this represents in terms of a gaming situation like that. But that could be it. So we have these different pieces that are fairly consistent in those spots, and then it has other behaviors as you go forward in the process. So we can find the area or the total that way, and this would give us whatever that total is. And I'm not really concerned with the number on this one as much as getting the idea across. So we can split this up into multiple pieces and look at each individual part that makes a little bit more sense, and then add all the pieces together at the end. I hope this was helpful. Please let me know if you need additional comments or additional explanations on this, and keep me posted on what is good and what you still need help with. Take care.